In this tutorial, we'll look at Euler rotations and gimbal lock to see how strange motion can occur in between keyframes. In the last video, we saw that Euler rotations have a rotation order that can be changed with x, y, z values. We'll explore this further with a quick example of setting up the rotation order of an object to avoid gimbal problems. So how does Euler work? This gimbal machine shows us. Each part is linked to one another, so when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, how 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane. Let's make this ourselves in a hierarchical system. To demonstrate, we'll grab some torus objects. They can represent each axis. Green will represent Y, X will be red, and Z blue. So altogether we have 3 toruses and an arrow object. Let's parent them together. X to Y, Z to X, and the arrow to Z. This is going to mimic a rotation order of Y, then X, then Z. The Y, or green torus, is at the top of our hierarchy. So in this parent structure, everything rotates with it. Z, on the other hand, affects the arrow, because it's at the bottom of the hierarchy, or the last axis in the rotation order. X is second in the rotation order, so it'll affect Z below. And see how Y stays still, because it's at the top of the hierarchy. Now here's where things start to get interesting. If we continue to rotate X in the middle of the hierarchy, it'll cause Y and Z to align. Here, this rotation order hits gimbal lock when 2 axes align. If we're animating, and our next step is to turn the arrow down, there's a problem, because there's no axis to turn on. Here's the missing axis, in grey. It's always possible to rotate our arrow into any new rotation, but we'll have to rotate all 3 axes to achieve it. Let's undo this and rotate all axes at once. Notice how the arrow doesn't rotate in a straight direction. Instead, it moves in an unexpected arc. This is the cause of gimbal problems in animation, because the object can move unexpectedly in between keyframes. A solution is to use a different parenting structure. This will change the arrow's rotation order. Our new order will be Y first, then Z, then X. In our new hierarchy, Y is still the parent, but X and Z have been swapped. Now we can rotate the object without hitting gimbal lock. In between, the arrow rotates as expected. But the gimbal problem doesn't go away, it just changes. With Euler, gimbal lock will always occur in some situation. There's just no way around it. In this example, gimbal lock still happens by turning the Z-axis 90 degrees to cause the X and Y axes to align. In another parent structure, the rotate order might be Z first, then Y, then X. Now gimbal lock occurs when the Y-axis rotates 90 degrees. Altogether, there are 6 parenting combinations to choose from. In each case, gimbal lock occurs on the axis of the parent, when the middle axis is rotated too far. Let's explore this in a real animation situation. Here's a 3D camera. We'll use the 3D software Maya as our example. In Maya, the rotation order is written backwards. In this case, Z is the parent, Y is below, and X is the child. Z here represents the role, or bank of an object. In this order, Z is at the top of the hierarchy. Y is in the middle, so when it's rotated, it won't affect Z. This axis can be referred to as yaw, heading, or pan. The bottom of the hierarchy is X, and in this example it's pitch or tilt. As soon as the camera looks sideways, we achieve gimbal lock. This isn't good, especially considering that the camera will frequently look to the side. In this scenario, it's difficult to roll the camera because Z, our roll axis, has been aligned with X, our tilt axis. If we switch to local object rotation mode, our manipulator will snap to the intuitive way of rotating the camera. But remember that this is only a visual guide. It simply makes it easier for us humans to rotate the camera. Under the hood, the software package is still using the Euler system, even if it doesn't appear that way. To demonstrate, let's roll the camera a little. Now we'll switch back to the Euler rotations and see what's actually happened under the hood. As we can see, the software, in this case Maya, has rotated the object with Euler rotations. In fact, it's always calculating in Euler, whether we like it or not. It's done this automatically and behind the scenes, matching how we turn the object using our local object manipulator. Euler is actually the correct display of how the computer sees the object. In this case, our camera's rotation. And this is all okay until we go back to the camera rotation before it was rolled. In this animation example, the camera isn't rolling on one axis. It's actually changing the values of two axes at once. This causes the camera to skew strangely in its rotation, and not just roll along its length. Let's reset and see if we can find a better rotation order. With any object, the key is to find a rotation order that has the least chance of hitting gimbal. So the trick here is to find the direction that the object is least likely to face. In this case, a camera rarely looks up or down. So we'll make the parent axis Y. A camera usually doesn't bank much either, so we want the bank axis, or Z, to be the child. So in Maya, a good camera rotation order is Y as the parent, X, and then Z. Now when we look sideways, we have no gimbal. The camera can tilt up, and we can still bank the camera without any hiccups. Even in situations where the camera looks up, this rotation order still works well. We'll finish with this example. A camera tracking up to follow a ball.